All right, today we're going to crack open a really powerful tool for making sense of a very messy and complicated world, Bayesian belief networks. And these are so much more than just diagrams. They're like these smart, dynamic maps that help us reason about, well, pretty much anything, from catching a cold to understanding huge financial markets. So let's dive right in. And that really is the million-dollar question, right? How can you take what looks like a simple flowchart and actually use it to make some pretty sophisticated predictions, especially when you don't have all the answers? We're going to find out by building one together, right from scratch.
You know, the easiest way to get your head around a Bayesian network is to think of it as a map of influence. That's all it is. It's a picture that shows you, just at a glance, how different things in the world are connected, and crucially, how they affect one another. Okay, so to make this feel a little less abstract, let's use a super relatable example, one I think we've all unfortunately experienced. We're going to map out the causes and effects of a plain old common cold. So the very first piece of our map is something called a node, and a node is just a variable or an event. It's one little piece of the puzzle. For us, the main event, our first node, is having a cold. Simple as that. And the next piece, that's the arc. The arc is just the arrow that connects two nodes. This is literally how we draw the lines between the dots on our map. It's showing us the pathway of influence from one thing to another.
Now, this is super important. The direction of that arrow means everything. If the arrow points from having a cold over to sneezing, that means having a cold causes sneezing. It's a one-way street. Sneezing doesn't turn around and cause you to have a cold. Okay, so now let's get to a really crucial rule, a rule that gives these maps all their power. And it's a very simple, but very strict rule about how you can draw these arrows. You could call it the no going back rule. Now, the fancy official term for this kind of structure is a Directed Acyclic Graph, or a DAG for short. Let's just break that down real quick. Directed just means the arrows point in one direction. And acyclic, well, that means without cycles. You can't start at one spot, follow the arrows around, and somehow end up back where you began. No loops.
So what does this actually look like? Well, a valid path is just a straight line. A cold causes sneezing, which might make your cat annoyed. Simple. But an invalid path would be one that loops back on itself. A can't cause B, which causes C, which then causes A again. And this whole no loops thing, it's not just a neat little rule. It's the key that unlocks the network's secret weapon, something called conditional independence. All that means is that an event, like sneezing, only really cares about its direct parents, in this case, whether you have a cold. That's what keeps the math from totally exploding when these maps get huge.
All right, so we've got our map, we know what influences what, but that's only half the picture, isn't it? A cold can cause sneezing, but how likely is it? How strong is that connection, really? And this is where things get really cool. This is where we add the numbers, where we bring in the magic of probability to turn this simple drawing into a full-blown reasoning engine. First things first, we have to start somewhere. And we start with the nodes that are at the top of the chain, the ones with no arrows pointing at them. We call these root nodes. And for these, we just give them a prior probability. It's just a fancy way of saying its general baseline chance of happening out in the world. So for our cold example, let's just say that on any given day, there's about a 5% chance that any random person has a cold. That's it. That's our prior probability. It's our starting point for everything else. Okay, but what about the other nodes, the ones that do have parents? Well, their chances depend on their parents, and we capture that relationship in something called a conditional probability table, or a CPT. Think of this table as the brain of the relationship. It holds all those if this, then that probabilities. And this table, right here, this is really the heart of the whole thing. Look at this. It's telling us that if you do have a cold, there's a whopping 90% chance you're going to be sneezing. But if you don't have a cold, well, that chance plummets down to just 15%. See? The network now understands the actual strength of that connection. So, okay, we've just built a teeny tiny little two-node network. But don't let that fool you for a second, because these exact same fundamental building blocks, they're all you need to model unbelievably complex systems. Let's see how this really scales up. Seriously, every single massive, mind-bogglingly complex Bayesian network you will ever see is built from these three simple things. Nodes for the events, one-way arrows with no loops showing the influence, and a bunch of probability tables to put numbers on it. That's the whole shebang. And boom, this is what that looks like in the real world. This is a system called Mentor.
and it's used to predict health risks in newborn babies. It looks insane, right? A total spider web. But I promise you, it's built using the exact same simple rules we just used for our little cold and sneezing example.
Okay, so why does any of this matter? Why go to all the trouble of building these crazy-looking maps? Because they're being used right now, a lot of times behind the scenes, to make way better decisions in some of the most important fields you can imagine.
Well, because the applications are just staggering. I mean, this isn't some academic toy. They're used in hospitals for tricky diagnoses, by banks to figure out credit risk. They even help your phone understand what you're saying. And get this, they've been used to squash bugs in Microsoft Windows and to help your mechanic figure out what's wrong with your car. They are absolutely everywhere. Some of the pioneers in this field, Collar and Friedman, really hit the nail on the head when they said the key is the separation of knowledge and reasoning. Think of it this way. The knowledge is your map of the world, the nodes and the probabilities. The reasoning is the engine that does the math on that map. And because they're separate, you can update your knowledge. You can add new data, tweak your probabilities as you learn more, without having to junk the whole engine and start over. It's incredibly flexible.
So I guess I'll just leave you with this question to chew on. Our lives are just tangled webs of cause and effect, right? So many influences that are totally invisible to us. These networks, they give us a language to actually draw those maps, to put numbers on the connections, and to see the hidden probabilities that shape our world. So think about it. What are the hidden maps shaping your world? And what would change? What could you do if you could actually see them clearly?